Let's jump right into a hidden battle taking place inside the machines we rely on every single day. It's the classic clash between mathematical perfection and physical reality. We engineers absolutely love clean lines, perfectly balanced equations, and a theoretical ideal. But the factory floor? Yeah, it's a completely messy, chaotic place. Today, we're going to see exactly how we bridge that massive gap in this explainer on mechanical couplings. Okay, so look at the central conflict here. In our perfect, ideal world on the left, we've got rigid couplings. These guys are built for absolutely zero misalignment. No shocks, just pure, unyielding, raw torque driven through direct mechanical shear and friction. It's geometric perfection. But then, on the right, reality hits. The real world demands flexible couplings. See those glowing orange waves? That's dynamic force. Real-world machinery needs elastomeric deformation, which is really just a fancy way of saying it needs engineered flexibility to survive all the thermal expansion, the shocks, and the shifting. It's a constant tug-of-war. Section 1. Foundation of the ideal. Let's look at the absolute simplest way to join two collinear shafts, the muff coupling. Putting a muff coupling together is this beautiful, elegantly linear process. Step 1, you line up your input and output shafts end-to-end perfectly. Step 2, you drop a solid sunk key right into the shared keyway slot. And step 3, you just slide a solid hollow sleeve right over the joint to lock the whole thing together. Conceptually, it just doesn't get any cleaner than this. What's super cool here is how the theoretical math literally becomes the metal in front of us. Take a look at that formula for torsional shear stress. That math directly dictates the exact thickness and strength that hollow sleeve has to have to keep the power flowing smoothly. All those variables, they literally guarantee the system holds, as long as the math holds. But here's the catch. This theoretical perfection hits a massive roadblock the second you step onto an actual factory floor. Think about it. A solid sleeve means you literally have to slide it horizontally over the ends of the shafts. So what happens if you're trying to connect a multi-ton electric motor to a gigantic gearbox, and they are both permanently bolted to a concrete floor? You simply don't have the space to slide a huge piece of solid metal back and forth. This blueprint perfectly captures the nightmare. Trying to assemble a solid coupling in a tight clearance zone between heavy housings, like you see in that red warning box, gives you a critical error. There's just not enough clearance. You physically cannot back the sleeve up to drop it over the joint without unbolting and moving heavy machines, which completely wrecks your perfect alignment. So to keep that alignment intact, we need a totally different approach. We've got to split it. Enter the clamp coupling. This totally flips the assembly process. Instead of a solid tube, the sleeve is sliced right down the middle. To lock it tight, we use vertical tightening bolts. As you crank those bolts down, you create this immense, crushing radial friction, that's what those inward-pointing blue arrows are showing, that just aggressively grips the shaft surface. And, just to be absolutely sure it doesn't slip, there's a mechanical sunk key in there too, acting as a secondary lock. To really get why this works, you have to understand friction torque. It's exactly what it sounds like. It is the twisting rotational force capacity generated entirely by how incredibly hard those split cast iron halves are squeezing down onto the steel shaft. Let's map that to the engineering calculation. At the bottom of the equation, you've got P, which is the downward clamping force from those bolts. That downward pull creates the friction, and that friction directly equals your friction torque capacity, which is that twisting blue arrow you see on the shaft. You are literally taking the linear pull of a tightened bolt and turning it into the rotational driving force for an entire factory. It's brilliant. Now, when you need maximum, unyielding torque transfer, and you can't just rely on friction, you bring in the heavy weight, rigid flange couplings. The secret to their perfect alignment is a precision spigot and recess joint on the left. It's a male-female connection that guarantees absolute collinearity. And if you check out the blueprint on the right, it's all about proportional engineering geometry. The master variable is the shaft diameter, D. That one single measurement dictates every single flange proportion. Hub outer diameter, exactly 2D. Pitch circle for the bolts, 3D. It scales perfectly. But then reality hits. The ideal world of perfect alignment and temperature control rarely survives out in the wild. When reality crashes in, we get hit with destructive physical forces that perfectly rigid couplings just aren't built for. We're talking lateral misalignment, where the shafts remain parallel but are physically offset. We see axial misalignment, where massive thermal expansion literally pushes the shafts together or pulls them apart.
And we've got angular misalignment, where the shafts intersect at a dangerous angle. The consequences? Absolutely devastating. If you force a totally inflexible, rigid flange to take on these real-world forces, it's catastrophic. Look at those glowing red, shattering cracks. Whether it's lateral offset, thermal expansion pulling the joint apart, or an angular intersection, the result is exactly the same. The unyielding forces will quite literally tear the coupling, blow out the bearings, and eventually destroy the machine itself. To survive all this chaos, engineers had to compromise on that pure rigidity and design the bushed pin coupling. Check out this exploded view. We threw out the rigid, unforgiving bolts. We swapped them for a solid steel pin, but the real genius is what's in the middle, a resilient rubber bush lined with a brass sleeve. That rubber acts as your primary shock absorber. It can soak up to 0.5 millimeter of lateral offset and 1.5 degrees of angular deflection, while the brass lining stops the rubber from wearing down internally against the steel pin. Because of this flexible bridge, the way power actually moves through the machine totally transforms. It doesn't just shear straight across anymore. It starts at the input shaft, moves to the input flange, and then it literally compresses into that flexible rubber bush. From there, it transfers to the brass-lined seal pin and finally drives the output flange. Follow those glowing blue arrows, and you can trace that exact dynamic power path. You can see how the force weaves its way in, compresses against the rubber bushes, and finds its way out. That compression, that's exactly where the magic happens. It's absorbing violent vibrations and sudden shocks before they can ever cross over and shatter the fragile output shaft. It is a highly localized sacrifice of rigid perfection just to keep the whole system alive. But adding flexibility gives us a totally new math problem. Because the rubber intentionally flexes, the steel pin isn't just being sheared anymore, it's actually being bent. Look at how the mathematical variables map to the physical dimensions of the pin right there on the screen. The bending moment relies on this crucial structural gap. You see that constant 5 in the formula? That matches perfectly to the engineered 5 millimeter clearance gap between the two flanges. The geometry and the equations are fundamentally linked to make absolutely sure that steel pin doesn't snap when the rubber yields. So, how do you make sense of all these choices? We use a master selection framework. It's basically a cheat sheet for engineers. Got a simple line shaft and room to move machines? The muff coupling is perfect. Trapped in tight clearances? Split the shell and grab a clamp coupling. Running perfectly aligned heavy machinery that needs max torque? The rigid flange is your go-to. But if you're hooking up an electric motor to a pump, where vibration and misalignment are basically guaranteed, you absolutely need the resilient, shock-absorbing bushed pin. Ultimately, it all comes down to this. Design starts in the ideal world for pure, unyielding power, like the rigid flange on the left. But a design proves its actual worth in the messy reality of the factory floor, perfectly embodied by the dynamic bush pin connecting the motor to the pump on the right. Two brilliant connections for two very different realities. So next time you're walking through a plant or just listening to some heavy machinery humming away, take a closer look at the joints. Ask yourself, what invisible battle between perfect geometry and messy reality is happening inside that connection? Are you looking at a rigid mathematical ideal or a beautifully flexible compromise built to survive the real world? Thanks for hanging out with me for this explainer. Keep questioning the mechanics around you, and I'll catch you next time.